Good morning everyone, I'm Moni from Basic Chemistry Honors first year. Today I'm read a Thermodynamics chapter. It is a visual impaired video, so we read the chapter Thermodynamics. Chemical energy stored by molecules can be released as a heat during chemical reactions when a fuel like methane, cooking gas or a coal burns in air. The chemical energy may also be used to mechanical works when a fuel burns in an engine to provide electrical energy through a galvanic cell like dry cell. Thus, the various forms of energy are interrelated and under certain conditions. This may be transferred from one form into another. The study of this energy transformation forms the subject matter of thermodynamics. The law of thermodynamics deals with energy changes of a macroscopic system involving a large number of molecules rather than microscopic system containing a few molecules. Thermodynamics is not concerned about how at what rate these energy transformations are carried out, but is based on the initial and the final state of the system undergoing the stage. Law of thermodynamics apply only when a system is in equilibrium or move from one equilibrium state to another equilibrium. For macroscopic properties like pressure and the temperature do not change with time or for a system in equilibrium state. In this unit, we would like to answer some important questions through the thermodynamics, like how do we determine the energy changes involved in a chemical reaction or a process? Will it occur or not? What drives the chemical reaction properties? To what extent do chemical reactions proceed? Thermodynamic terms, we can interested in the chemical reactions and the energy changes accompanying them. First, we need to know certain thermodynamics terms. These are discussed below. The system and the surrounding. A system in thermodynamics refers to that part of universe in which observations are made and the remaining universe constitutes the surrounding. The surrounding includes everything other than system. System and the surrounding together constitute the universe. The universe is equal to the system plus the surrounding. However, the entire universe other than system is not affected by the changes taking place in the system. Therefore, for practical purposes, the surroundings are that a portion of remaining universe which can interact with the system. Usually, the reason of a space in the neighborhood of a system constituting surroundings. Types of a system. We further classify a system according to the movement of matter and energy out of the system. Open system. In an open system, there is the exchange of energy and matter between system and surrounding. The presence of reactants in an open vehicle is an example of open system. It is a closed system. There is no exchange of matter, but exchange of energy is possible between system and surrounding. Isolated system. It is an isolated system. There is no exchange of energy or a matter between the system and the surrounding. The states of the system. The system must be described in order to make any useful calculation by specifying a quantity. Each of the properties such as its pressure, volume and the temperature as well as the composition of the system is before and often to change. You would recall from your physics course that if the state of the system in the machine is completely satisfied at a given instant of the time. The states of thermodynamic system is described by a numerical or a macroscopic property. We can describe the state of a gases by quoting its pressure, volume, or a temperature and amount. The variables like P, V, T are called the state variables or a state function because the values depend not only on the states of the system and not on how it's reached. In order to complete define the states of the system, it is not necessary to define all the properties of system, as only a certain numbers of the properties can be verified independently. The numbers depends on the nature of the system. Once these minimum numbers of the macroscopic properties are fixed, the internal energy of the states of the function. When we talk about the chemical system, losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy. You may think of the sum of these energies of the system in thermodynamics. We call it the internal energy use of the system, which may change when heat passes into or out of the system. Work is done on or by the system. Matter enters or leaves the system. Let us first examine the changes in internal energy by doing work. We take a system containing some quantity of water in thermos flask or an insulated beaker. Thus, would not allow the exchange of heat within the system and the surrounding through its boundary, and we call this type of system aerobatic. Heat. We can also change the internal energy of a system by transfers of heat from the surrounding of the system or vice versa without expenditure of work. The exchange of energy, which is the result of the temperature difference, is called heat Q. Let us consider bringing about the same changes in temperature, the initial and the final state as before in the section by transfer of heat through thermal conducting walls instead of adiabatic walls. By convention of IUPAC is chemical thermodynamics, the Q is positive when heat is transferred from the surrounding to the system and the internal energy of a system is increasing, and the Q is negative when heat is transferred from system to surrounding, resulting in decreasing of the internal energy of the system. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transferring of heat. We write changes in internal energy of the system as delta U is equal to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W is equal to delta U will depend only on the initial and the final state. It will be independent of the way the change is carried out. If there is no transfer of energy as the heat as the work, if W is equals to W equals to 0 and Q equals to 0, then delta U is equals to 0. Delta U is equals to Q plus W is a mathematical statement of the first law of thermodynamics. The energy of isolated system is constant. Work. First of all, let us concentrate on the nature of the work a system can do. We will consider only mechanical work, pressure volume. For understanding the pressure volume work, let us consider a cylindrical volume which contains 1 mole of ideal gas fitted in a fractionless piston. Total volume of the gas is V1, V initial, and the pressure of the gas is inside is P. If external pressure is P external, which is greater than P, piston is moved inward till the pressure inside become equal to P external. Let this change be achieved in a single step and the final volume E by Vf. During this comparison, suppose the piston moves a distance L and its cross-sectional area is A of the piston. As the volume changes, L into A is equals to delta V. You also know pressure is force for area. So therefore, force on a piston P external equals to A. If W is the work done on the system by movement of the piston, then W is equals to force into displacement. A process or a change is said to be reversible if a change is brought out such a way that its process could at any moment by reversed by infinite stimulus changes. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always near equilibrium with each other. Process other than reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if it relates the work from the internal pressure of the system. We can relate work to the internal pressure of the system under reversible conditions by writing equation 5.3 as follows. Since dp equals to d into dtv very small, we can write equation 5.4. Now the pressure of the gas can be expressed in terms of its volume through the gas equation. For n moles of an ideal gas, P is equals to nRT divided by V. Therefore, at constant temperature, W reversible is equals to minus nRT in Vf by V. I. Free expansion of the gas in a vacuum is called a free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Now we can write equation 5.1 in number of the ways depending on the type of process. Let us substitute W is equals to minus P external del V in the equation 5.1 when we get delta U is equals to Q minus P external delta V. If a process is carried out a constant volume, delta V is equals to 0. The subscript V and QV denotes that heat is applied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, the constant expansion of ideal gas into vacuum, W is equals to 0, since P external is 0. Also, Joule determined experimentally that Q equals to 0, therefore delta U equals to 0. Equation 5.1 delta U is equals to Q plus W can be expressed for isothermal, irreversible and reversible changes as follows. For isothermal irreversible changes, Q is equals to minus the W. For isothermal reversible changes, Q is equals to minus W equals to nRT. Log V final by V initial. For the adiabatic change, Q equals to 0, delta U is equals to W even. Enthalpy H, a useful new state function. We know that the heat absorbed at constant volume is equal to change in the internal energy, delta U is equal to QV. But most of the chemical reactions are carried out not at constant volume but in a flask or a test tube under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equations as delta Q is equals to Qp minus P delta V at constant pressure. Where Qp is the heat absorbed by a system and minus Qp delta V represent expression works done by the system. Let us represent the initial state by subscript 1 and final state by subscript 2. We can write the above equation as U2 minus U1 Q2 minus P. Delta is negative for exothermic reaction which evolves the heat during the reaction, and delta H is positive for endothermic reaction which absorbs the heat from its surrounding. In thermodynamics, a distinction is made between extensive properties and intensive properties. An extensive property is a property whose values depend upon the quantity and the size of matter present in system. For example, mass, volume, internal energy, enthalpy. Those properties which do not depend on the quantity or the size of a matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. In subsections, let us see how to measure heat transfer to a system. The heat appearance is a rise in the temperature of the system in case of heat absorbed by the system. The increasing temperature is proportional to the heat transfer. Q is equal to coefficient into delta T. The magnitude of coefficient depends on the size, composition, and nature of the system. We can also write it as a Q is equal to C delta T. The coefficient C is called the heat capacity. C is directly proportional to the amount of substance. The molar heat capacity of a substance is C by M. It is the heat capacity for 1 mole of substance and the quantity of the heat needed to rise the temperature of 1 mole by 1 degree Celsius. Specific heat, also called the specific heat capacity, is the quantity of the heat required to rise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out heat Q required to rise the temperature of a sample, we multiply the specific heat of substance C by the mass M and the temperature changes delta T as Q is equal to C rho into M into delta T is equal to C delta T. The relationship between Cp and Cv for the ideal gas. We can write equation of heat Q at constant volume as Qv is equal to Cv delta T equals to delta U at constant pressure as Qp Cp delta T equals to delta H. The difference between Cp and Cv can be derived for an ideal gas as for 1 mole of an ideal gas delta H is equal to delta U plus mu P delta V delta E equals to delta U plus mu delta RT. Equation 5.12 delta H is equal to delta U plus mu R delta 3 and put in the value delta H and delta U. Cp minus is equals to R. The measurements of the delta U and delta H calorimeter, and this is the measurement in the calorimeter. The enthalpy change occupying a reaction is called the reaction enthalpy. The enthalpy changes of a chemical reaction is given by a symbol RH. The standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances are their standard state. The standard state of a substance is the specified temperature. It is a pure form at ethanol at 298 Kelvin is pure liquid in ethanol 1 mole. Standard states of the solid iron 500 Kelvin in pure iron 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by addition to the symbol delta H. Enthalpy changes during the phase transformation. The enthalpy changes that take place the melting or the 1 mole. So a solid substance's standard state is called the standard enthalpy. Fusion fusion. Standard enthalpy changes of a fusion in the vaporization reaction. The amount of heat required to vaporize 1 mole of a liquid at a constant temperature and understanding pressure it is called standard enthalpy of vaporization and molar energy utilization. Standard enthalpy of sublimation is the change of the enthalpy when 1 mole of a solid substance symbolized at a constant temperature and under standard pressure equals to 1 bar. It is important to understand the standard molar enthalpy formation. We have 1 mole of the compound is formed from the constituent elements and it is about 3 quantities and of each water interchanges products of a reaction.